In this video, we're going to discuss initial quantum theories, namely the wave-particle duality and the de Broglie wavelength. And the second one is the Heisenberg uncertainty principle. So let's start with the wave-particle duality. So earlier in the chapter, we discussed the experiment that Einstein conducted, which is the photoelectric effect, and discovered that in addition to light traveling as a wave, it had a particle-like nature. And we talked about photon, and this is where the wave-particle duality of light comes from. But based on that work, de Broglie collaborated with Einstein to develop an equation that is proposed for mainly small particles. So it can be electrons or even neutrons, aka subatomic particles. And this equation is right here, where the wavelength equals to Planck's constant divided by its mass times velocity. Now, de Broglie's equation, it applies to any matter. So it's not just subatomic particles, it's also larger or macroscopic objects such as a baseball or a golf ball. It just does not make that much impact because larger objects such as a car, for example, has a very small wavelength. Now let's move on to problems, and I will show you two types of problems. So I get to do this problem, and then you get to do the second type of problem, and I will explain how the difference in de Broglie wavelength does not make sense for a larger object. So in this question, what it says that what is the de Broglie wavelength of an electron moving at 1/10 of the speed of light? And you're given the mass of the electron right here. So let's see. We have here the de Broglie wavelength equals to Planck's constant divided by mass times velocity. All right, therefore equals to 6.626 times 10 to the negative 34. And this right here has infinite sig figs. And the units are kilogram, meter squares over second squared, divided by the mass. So this is mass, which is the mass of the electron, which is 9.109 times 10 to the negative 31st kilograms. And this here has 4 sig figs times it tells you it travels at 1/10 of the speed of light. So here is 1 over 10 or 0.1 times 2.998 times 10 to the 7th. This also has infinite sig figs. And in this case, I get 2.42632.571 times 10 to the negative 11 meters. And if I'm rounding to 4 sig figs, this gives me 2.426 meters. Oh, sorry. Times 10 to the negative 11th meters. Now, I want you to calculate on your own what is the de Broglie wavelength for something like a tennis ball. All right, so I'm going to work it through also like I did with the other problem. So you have the mass of the tennis ball is 55 grams and its speed is 35 meters per second, and it wants you to calculate it in nanometers. So in this case, I'm going to compare it first in meters and then I'm going to convert it to nanometers. But let's see. So we have here wavelength equals to Planck's constant divided by mass times velocity, and this equal to 6.626 times 10 to the negative 34 kilogram times meter squared over second squared divided by the 55. Remember here, this is in kilograms, so I have to convert this also to kilograms. times the 35 meters over seconds. I have the units here in meters and then seconds, so the units check out, and this gives me, so let's check for sig figs. This is infinite, this is 2 sig figs, and this is 2 sig figs, and I have here 3.442077792 times 10 to the negative 34 meters. Now, note that something that is macroscopic, its wavelength is super, super small compared to something like an electron, right? Which its wavelength makes sense. Okay, so if I convert this, for example, to nanometers, so I have here 10 to the 9th nanometers in 1 meter, and I'm calculating this right now with you. So give me 1 second until I plug it in. 426 e to the negative 11 times 1 e to the 9th. And this gives me 0.02426 nanometers. Okay. Now, if I convert this answer right here that I have to nanometers, the 3.4 to the negative 34th. Me 1 second. I'm calculating it. Okay. Okay. So I have here 3.44 to the negative 34th times 1 e to the 9th. And this gives me 3.4, because I'm rounding here to 2 sig figs, times 10 to the negative 25 nanometers. So still really, really, really small. So it doesn't make sense. Now, moving on to uncertainty principle, or the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle states that it is impossible for us to know the absolute certain position and the momentum, okay? The momentum here, which is mass times velocity of an electron or any subatomic particle. And the reason for that is electrons actually and subatomic particles like neutrons, etc., have a wave-like nature. Okay, so they have a wave-like nature and they travel in a wave-like nature. So with that being said, that means that they are spread out over space if they have a wave-like nature. So it is very hard to pinpoint this exact location of the electrons now, or the subatomic particles. And with that sense also, it's very hard to exactly determine the momentum of these subatomic particles, because really they are not just one wave. The electron, for example, is not just one wave, it's an average of many waves, when each wave in this average has its momentum. So we can say there is a range of momentum and a range of location rather than an exact location and exact momentum. And with that sense, Heisenberg proposed this particular equation right here for his proposal, and said that delta x, which is the uncertainty in position, equals to the uncertainty in the uncertainty in momentum, which is here the mass, times the change in velocity, is greater than or equal to Planck's constant divided by 4 times pi. Now, let's see how this applies the uncertainty in position to something that is very large, like Superman, for example, versus an electron. So something, let's think about this conceptually. So something that is very large, like a human body, or like, again, a baseball or a tennis ball, because of its size, you can determine with certainty its position, and its location at the same time. Its location and its momentum. But for something very small, the uncertainty will be very, very, very large. So let's see. In here, Superman has a mass of 91 kilogram and is traveling at 1/5 of the speed of light. And if the speed of Superman that he travels with is with a precision of 1.5%, what is the uncertainty in his position? Okay, so let's look at this. So we can say that delta x times mass change in velocity is greater than or equal to Planck's constant over 4 pi. And if we arrange, because we're solving for the uncertainty, therefore I can say that delta x equals to h divided by 4 pi times m delta v. And we know that Planck's constant is 6.626 times 10 to the negative 34 kilogram times meter squared over second squared divided by 4 pi times the mass. The mass here is 91 kilograms times, now Superman travels at 1/5 of the speed of light. So I can say that I have here 1/5 times 2.998 times 10 to the 8th meter per second, but also says that the precision with a known precision of 1.5%. So I'm going to multiply this also by 0.015 because the speed has this precision. Okay, and this, again, let's track our sig figs. We have here infinite sig figs. This is also infinite. I have here 2 sig figs and 2 sig figs. So my answer should end up with 2 sig figs. So 6.44239416 times 10 to the negative 34 meters. Okay. So in this case, I can say that if there is really very, very tiny uncertainty in Superman's position because it is a larger object. Now, I want you to solve for the uncertainty in a position of an electron, okay, and compare it to the previous question right there. So we have here a 12 electron volt electron can be shown to have a speed of 2.05 times 10 to the 6, and assuming the precision value right here is 1.5%, what is the maximum precision that we can locate the position of the electron? So I forgot to put the mass of the electron, so we can say that the mass of one electron right here is 9.109 times 10 to the negative 31st kilogram. Again, we're going to use the same equation. Let me copy and paste it from the slide right here. And I can say that we have it. Okay, so therefore, if I, again, rearrange, it'll be h over 4 pi times mass times a change in velocity, okay, which equals to 6.626 times 10 to the negative 34 kilogram times meter squared over second squared divided by 4 pi times 9.109 times 10 to the negative 31st kilograms. So I have here 4 sig figs, okay, and times the change in velocity. So the change in velocity right here, you have the speed, which is the 2.05 times 10 to the sixth, okay, times the precision, which is 0.015. So right here I have the smallest number of sig figs is 2. This is infinite sig figs. This is infinite sig figs. So in this case, I can say that this is 1.8824599951 times 10 to the negative 9th meter. And if I round this to 2 sig figs, it becomes 1.9 times 10 to the 9th meter. So the uncertainty here is quite larger compared to the compared to Superman, because again, an electron is subatomic particle, and it's hard for us to be able to pinpoint its location